All right, a couple people asked me about the prerequisite topics and what they're supposed to know for this class in email. So it's hard to do this. I mean, because even though we know that the prereq is statics and calculus 2 and thermodynamics and dynamics, right? Dynamics, those classes, there's a lot of prereqs to those prereqs. So I just kind of lumped some functions, some min-max, how to find a root of a system of equations, how to differentiate, how to integrate, what's a dot product, what's a cross product, and a lot of other mathematical topics. And then for the statics and dynamics, what's a force, what's a vector, what's a moment of a force, what's the area moment of inertia, what's the mass moment of inertia, what's the equilibrium, what's a free body diagram. You should be able to handle distributed force fields, convert them to equivalent force fields, handle friction, slipping, and tipping so it becomes where it's not, moves out of the equilibrium condition and you're going to have slip or tip. Centroids of areas, centroids of volumes, both by integration to calculate it, as well as using composites to get the equivalent of an area or a volume which isn't so trivial. Yes?
Are we really going to calculate centroids?
Yes. Absolutely, positively, yes. Absolutely, positively, yes. Go back and review. Be able to do it. Area moment of inertia, mass moment of inertia, parallel axis theorem, and then I didn't even list all the dynamics topics, sorry. It's almost too much to really just give you one list. Say, be able to solve these 5 problems. It's a lot of backbone. All right, let's jump into a few examples. Can you solve this problem? Can you, given a function, and this is a very easy function, can you evaluate the integral of f of x between 1 and 2? I'm going to pause. I'm going to see if you can do it. There's the problem. It's really low order. It's really pretty easy, right? All right, so you should have gotten 11 halves, 5.5. Let's try another problem. Given this function, which is 9 times the natural log of 4x, evaluate the derivative of this function at x equal to 3. All right, a lot of people did it correctly. Some people are still, you just have to brush up. And then, again, I'll mention, please practice being very systematic in these easier problems so that you're systematic in the harder problems, such that if you do have a small error, you can get the most partial credit. But if I can't figure out your logic or your steps, then I can't award much partial credit if you unfortunately don't get the right answer. And what we're looking for is something like f prime at 3 is equal to 3. This problem has no units on the answer, but if there was, we'd put units there. So the box includes the equation. How many equal signs are inside the box? 1. How many students will give me 2 or 3 equal signs? They say, oh, he wants the answer in the box. There it is. No, don't do that. It's like the final answer with 1 equal sign, something on the left, something on the right of the equal sign, and when appropriate, units. Here's another function, y. Get location x in the range from 2 to 6 is the minimum value of y. So now we have a minimum. So if you say to find the location of the minimum value of the y, a lot of us in mathematician type of frame of mind would say, I'm going to take and find dy dx. True? For this problem, what is dy dx? Negative 4x plus the exponential of x divided by 1.7. All of that 1.7. True or false? Look good? Thumbs up? Did I differentiate that function correctly?
So you just take the constant from whatever x or which brings
well, it's one of these. I have e to the ax. What's the derivative with respect to x of e to the ax? A times e to the ax, true? So somebody says, well, this problem had x, over b, e to the x over b. Well, that's going to be 1 over b, e to the x over b is the, the derivative with respect to x. Right? Okay. So I think this is done correctly. Now, once we have that, we want to set that equal to 0, equal to negative 4x plus exponential of x divided by 1.7 divided by 1.7, and look for the root in this region here. A lot of times in your calculators, you will have to give it an initial guess, and so probably guess around 4. Don't start it at 0. Start it at 4, or 3, or 5. Start it in the range, and hopefully it's close enough, and it'll zone in. Another thing which you can do is you can make a plot of y as a function of x. Put in 2, put in 3, put in 4, put in 5, put in 6. And maybe this is positive, 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 negative, negative. What do you know? Yeah, it changed. Actually, I'm not plotting that. I should plot dy dx, right?
Well, that's like where the root is, right, in between 4 and 5.
Yes, that's where the root would be. Right. Or if you plotted y, it would be like this is, this is all increasing in this region, and then it's all decreasing in that region. I think I do have this plotted. Let me take a look. Okay, is that the same function that I just had? Yeah. And so I just take that function and I plot the function from 2 to 6. What did I use? Excel. Just so it's easy to visualize and make the calculations. What does that function from 2 to 6 look like? What's it doing? So unfortunately, if you do the mathematician's approach, where you differentiate that function, give it a guess and start looking for the root within that 2 to 6, guess where it's going to get? It'll get a value outside of the range. So in this case, what's the best answer for that problem? Where is the minimum of that function in the range from 2 to 6? At 6. So that's more of an engineer who would say, well, I need to make sure it's not at the ends of my range that I'm looking for. Does that make sense? All right. All right. What I did here was I changed that value right here. Instead of 1.7, put in 1.4. And just by changing that 1.4, guess what the function does? It gives us a nice minimum in the range. But if that constant was 1.7, the minimum of the function is outside of the range. Hence, the minimum is at the limit, one of the ends of the range. Yes?
So if you want to find the minimum, you take the derivative and do the thing you said, you plug in numbers, and it goes positive, 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 negative. Is like the number like right above that, the minimum, like right before it?
Well, let's do this. This is the function that's plotted. What would the df dx look like between 2 and about this number, which is 4.52 something? That's the root, 4.52 blah, blah, blah. I encourage you to plug this in and make sure you can solve a problem like this on your calculator. Right here, I've given you numeric values for the whole thing. But this is going to be negative, negative, negative. But when it gets right in here, it won't be as strong of a negative because it's about ready to go to 0. And then once it's at 0, then it's positive, positive, positive. So over here, it's positive, it's negative. Right there, it's 0. df dx is 0 right there. Make sense?
So the root is where it's negative or where it's minimum?
Well, we were looking for the minimum or the maximum. What did I word it? How did I word it? Looking for the minimum value of this function in that range. Hence, I take the derivative of that function and I set it equal to 0 and I solve for that root of that equation. And if it happens to be in the range, this problem it does, it's around 4.5, boom. That'll be either a minimum or a maximum. You can check the concavity, the second derivative, to see analytically, or just plot it. Plot it, evaluate it at some functions. Don't be afraid to take some time and work out a table like this. to make sure that you have confidence in your solution, okay? And be able to solve these type of problems. Let's move on to this problem. Again, this is just a review of some topics that we want to be able to solve. This is prerequisite material. There's a shape, this area. It's shaded blue. It's a two-dimensional problem. You can see the x-axis is defined, the y-axis is defined. That area is bounded by the y equal to 0, x going from 0 to 3. And then it's x is equal to 3, but y goes from 0. What's this value of y up here? Just look at the function, right? So it'll be the value of y up here will be 1/9 of 3 cubed. So what will that be? 3, right? Won't it be 3? Yeah. So, and then this is the other side that bounds that blue shaded area. Calculate the area for this shape. I'm going to pause. I'm going to see if you can do that. I want you to calculate the area for this shape. All right, so how many people are able to get for the first part? The area is 2.25 meters squared. Good. Now for the second part of this problem. What is the centroidal x location? What do you mean? Well, this has a centroid. A lot of times they put a symbol maybe like this for the centroid, or I don't know, something, right? This is the centroid of the area, right? And here, where do you think the centroid of the area is? Closer to in this region, closer in this region, closer in this region? No, it's going to be right in the kind of the balance point, isn't it? So what would be the answer for part 2, roughly? Roughly. You're going to start off mathematically. You're going to solve for it. But I'm going to help you a little bit with the engineering frame of mind. If somebody says, oh, I'm going to come back and I have this x bar is the centroidal x location of the centroid, right? And I'm going to find that it's 9 meters. What do you think? No way. It's greater than 3. It's going to be less than 3, isn't it? Somebody says, oh, it's -9. It's wrong. It's wrong. It's not going to be less than 0. It has to be in the shaded area. Okay? What do you think roughly? Just guess. What do you think the answer is going to be just visually looking at it? 2.5. Right? So you could, that's around 2. It's probably a little more 2, 2.5. Look good? If you don't get an answer, roughly around 2.5, look for an error. But now begin the process of calculating this x bar. And then later we could ask, what is y bar? But that's not been asked right now. Don't calculate it. Just calculate x bar. The x location of the centroid of that area. Professor, I need a cheat sheet. You don't need a cheat sheet. All right, well, what's the equation to find x bar? What's the basic equation that you have to remember? Let's do this. What was the equation that you used to calculate the area? Double dA. You did a double area integral. And what is a little increment dA? Dx times dy. Does it matter if I do y first and then x? No. But a lot of times you look at the problem and you go, you know what? If here's 1 times dA, and I have do a double area integral, I have 1 as an integrand, right? And I have to work out my lower and upper limits for y, or my lower and upper limits for x first. Okay, whatever makes sense. You should be able to do it both ways. How many people have enough experience to see which way would be a slightly easier, method A or method B for this problem? B. B would be. But A, you can work it. You can definitely work it. But what we do is we come out for method B. Let's try that one. We're going to go y. So for any location x, I have to be able to specify what's the lower bound of y and the upper bound of y for the inner integral of this double area integral. What's the lower value of y? 0. That's the easy part. What's the upper value? The equation that's given, which is 1/9 x cubed. Whoops.
Plug in x as 3 and solve for the actual, like do you plug in the actual upper limit? Yeah. Or do you just leave it as the...
No, this is the way you solve this problem. Let me finish it out and then see if I don't answer your question. Now, before I do that inner integral, think about what would be the limits on the outer integral, x. It goes from 0 to 3. And you say, okay, so what's this inner integral? The integral 1 times dy is just y evaluated 0 to 1/9 x cubed. And then I'm going to have that outer integral. I'm just copying it down, 0 to 3 dx. And then what we have is we have 1/9 x cubed integrate 0 to 3 dx. Some people said, I just jumped to that equation. Well, conceptually, you did a double area integral. Okay. All right. Now let's go back and now use that information to remind us, what is the equation to calculate x bar? Okay, I'm going to do this. I'm going to pause. I want you, from memory, to write down the equation for x bar, because that's kind of an important equation, the starting point to this problem, and if you don't get it, you're sunk. True? And I want you to struggle with it. All right, so you have to remember this equation. True? And sometimes they'll write it as a single area dA, sometimes a double area because it is an area integral. How many people, once they see it, that say, oh yeah, now I know it. Yeah, I see it. That's my old friend. Right? Somebody says for part 3, they want the centroidal y location. They want y bar. Is that the integral 1 over area integral y dA? Yeah? Yeah, sure, it is. So what do we have to do here is we already know the area, so we can leave this as 1 over whatever this area was, 2.25 meters squared. And then we're going to have the double area integral of x. Do you want to do dy dx? Do it in that order? And so will it have the same lower limit, 0 to 1/9 x cubed, and the same lower limit x goes from 0 to 3? How many students will forget to divide by area? Don't do it, right? Don't forget to divide by the area. And if you check your units, what is the SI typical unit for meter? I mean, so for length, meter, right, for x. And then dA, it would be meters squared. And then you divide by meters squared. And what is the units of x bar? Meters. Somebody wrote, I think x bar is equal to 1 over a, the integral of a dA. It's wrong. And one of the things that you can just look at, the units, it would be like, hold it. Meters squared integrated over meter squared divided by meter squared is going to not give me meters. It's going to give me meters squared. Somebody says, well, I think it's just 1 integral. I've seen that one too. Is it the 1 over a, the integral dA? Well, just look at the units. It'll be meters squared over meters squared. Guess what? Dimensionless. Is x bar dimensionless? No, it has to have units. We know it's around 2.5. Well, when you do the calculation, and I encourage you to do it, it will come in at 2.4 meters. How many people already did it and verified it's 2.4? Did you already do it? You did it already? Good. 2.4. Anybody else? One more? So there you go. Okay. You ready to move on to something a little more challenging? Hate to bring it up, but let's try it.
Are you posting all these videos online as well?
I'll try. For the distributed loading, calculate the equivalent resultant force and the location on the beam measured from point A. Where's point A? Right here. Measured from point A where the equivalent resultant force needs to be applied. To do what? To simplify this force system which has two distributed loads. They're triangular shaped, they're triangular profile for that distributed load. Meaning that you have 9 kilonewtons per meter intensity of the load right here, and then it goes down to 0 intensity at the distance, let's run x out to 4 meters, and then another part kicks back up to 9 kilonewtons per meter, and then it drops back down at 8 meters to 0. So you have a triangular distributed load. So two parts. What is the resultant force, the magnitude of it, and then where do I place it on the beam so that it is an equivalent force system. We're going to do a lot of things like this in this class. So what we do is we find out that you talk about FR1 and FR2, and the magnitude of FR1 is 18. Exactly right, 18 kilonewtons. How did you get 18 kilonewtons? The area? That's right. So basically it's you can do it a number of different ways. You can think about a uniform load that's always 9 kilonewtons per meter over a range of 4 meters, and then say, no, I don't have a uniform. I have only 1/2 of it divided by half. And then you'll get to 18 kilonewtons, true? So the 18 kilonewtons is the 9 kilonewtons per meter times 4 meters times 1/2. And then you have two 18 kilonewton loads. And so what's the total equivalent downward resultant force? 36. 36 kilonewtons. That way, the equivalent system has the same downward net force as the two parts which are made up of distributed loads. That now, part 2 is where do I apply it so it has an equivalent moment. The most logical place is the moment around point A because you're going to be measuring x from A. So we have a coordinate system that goes x, I already did it down here, out. And so where is FR1 applied? Is it applied right in the middle of that distributed load? No, 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 no. Where is it applied? 1/3 of the way because that's the triangular. The professor, I need an equation sheet to remember that. No, your colleagues don't. A lot of you don't, right? It's 1/3 of the way. From where? The peak. So where it is applied visually is around right there, which is at a location right here of x equal to 4 divided by 3 meters. How about for the second one? Right there. Where is that location? 4 divided by 3 meters plus 4 meters. 4 plus 4/3, true? Now that I know where each of those two are applied, I have the equation, the constraint, or the goal is to have the one force applied at a location, let's say F of R single times X, where you're going to apply that resultant, would create a moment around point A of the equivalent system, and I want that to have the same as the moment from around point A of FR1 and the moment about point A of FR2, which is the same as the moment around point A for the distributed loads. So this one is the FR1, the 18 kilonewtons, times the distance, 4/3 meter. And this one is the 18 kilonewtons times the distance 4 plus 4/3, all that meter. And then you just have x of r, this whole equation, this f of r you bring over. That f of r was 36 kilonewtons, true? And so you get the x where you're supposed to place it is at 3.33 meters. Is that what you got? Yes. All right, very good. 3.33 meters. True?
So you basically, you took a moment about some like imaginary place that would...
Well, it took it around point A. This distributed load creates a moment around point A. It's equivalent to this point load, FR1, applied at that location 4/3. This distributed load right here creates a moment around point A, which is equivalent to FR2 applied at this location 4 plus 4/3. And what I really want is I want just one, here's my beam again, one load applied at 3.33 meters. This is a 36 kilonewton load, and that has equivalent of both of the two steps. You go back to that one and then back to that one. So go with 2-point loads and then go back to the original distributed loads. Make sense? All right. Oh boy. For the given area, calculate the area moment of inertia about the y-axis. Well, where is the y-axis? Right here is the y-axis. How do I calculate that area moment of inertia, which a lot of textbooks use the symbol I, Y, Y. That's what I'm asked to calculate. Can you do it? I'm running out of time, but you need to be able to do it, and I want to give you a few seconds to do it, so let me pause. So what you have to remember is this is the double area integral, dA, and it's calculated as either x squared or the double area integral x dA, or double area integral 1 over a x squared dA, or the double area integral of y squared dA, or the double area integral y dA, or the 1 over a double area integral y squared dA. There's a lot of versions. I'm throwing out some candidates. How many candidates do I have here on this paper? 9 candidates. 9 candidates for what I'm asked to solve for, right? With that hint, I want you to write down the right form, and I want to check. All right, so I threw out 9 candidates for what this I sub yy is from memory. I know if we had an equation sheet, you just look it up. Hey, here it is. No, no, no. Let me ask this question to help guide you. If I took this area and I just made it look like this, would I sub yy change or not change? What we're doing is, I like to think of it as how they revolve around the axis of interest. I know there's a strong parallelism between the mass moment of inertia and the area moment of inertia. But if you have a large area away from the axis which you're revolving around, you get a large area moment of inertia. So if I look at this one, which has the same total area, is the area further away from the y-axis if you're revolving around the y-axis for this case B, you know, some other, it's closer. It's going to have a much smaller area moment of inertia. Let's do this one. Take this one and flip it like that. So I just took this area and I flipped it over the x-axis. Will it have the same IYY, the same area moment of inertia around the y-axis? Yes, it will. Yes, it will. Okay? So this one would have a much smaller IYY, would be much smaller than the original. How about if I flipped it like this? It would be even larger because it's further, the area, more of the area is further away from the y-axis. So I know that a few of you have the right answer, but some of you are toggling between, do I put x or y inside the integral dA? What is a measure of how far it is away from the y-axis? X, and that always throws me for a loop. You know, when I learned it and everything else way back when, it's like so confusing. So what's the correct equation? Isn't this the correct equation for I sub y? The integral of x squared. Hey, why isn't y squared? It's x squared. It's the distance from that axis, and it's the area moment, so you sum over the areas. Now, once you have that and you know how to do the area integral, dx, dy, I'm confident you can make the computation, okay? In the interest of time, let me just leave it alone. I'm looking at the clock. I got a lot to go, but you need to be able to calculate. What would be the SI units on that? Meter to the 4th power. Very funny units. Very funny units. All right. All right. For the given area, hey, we haven't left this problem yet, have we? Calculate the area moment of inertia about the centroidal y-axis. What? This is the y-axis right here. No. Do the parallel axis that goes through the centroid of my area. Where was the centroid of my area? Right around here. They want it around this axis. What's that called? That, to me, is called the centroidal axis that's parallel to the y-axis. So it's the centroidal y-axis. Sometimes they'll put I sub y bar, or I sub y sub c, y sub c. What does the subscript c or the bar on top mean? It's not the y-axis for the whole coordinate system. It's the centroidal. Sometimes they'll put I sub y prime, y prime. You just have to pay attention to what book you got, what book you're looking at. But there's a axis right here. It's the y-axis through the centroid of that area. How do I calculate that one? Would it be something like I sub y bar is equal to the integral dA of the distance? I almost introduce a new coordinate system, a local coordinate system. Call this the y prime and the x prime coordinate system. X prime squared dA? Let me ask you this. Would this value of I sub y for the centroidal y-axis be greater or less than the one I sub y for the coordinate system over here? Which one would be, or do they have the same? This would be much smaller. I sub y bar is, for this problem, much smaller than I sub y. Make sense? Guess where we're going now? What sort of axis theorem? Parallel axis theorem. Is there a mystery as to how they're related? I pause. How many of you can write down the parallel axis theorem?